So I started in 1993 here at UCL. This was my first choice of university, and I made many good friends here. It was a great time, and during that first couple of years at university, I actually got some new hobbies. I started gliding. That was one of my first interests, and I managed to fit in some study as well. So I went through my maybe years 1, 2, and 3 following the normal program. Attended some of the Good Society events like the Frank Morton Sports Day. That was very good, and many Ramsay dinners as well. It wasn't until the third year when I actually got an interest in something a little bit different. I was encouraged to do mathematical modelling as a research project with David Bogle. And that was a bit of a turning point in the career. That was a real interest which I sort of pursued right the way into the fourth year when I started doing a research project with Tim Elson on computational fluid dynamics. It was during that fourth year I decided that I'd like to go into postgraduate study and decided to apply for a PhD. At the end of the fourth year, I gave my first conference talk while still an undergraduate, based on the work I did in my third year. And I started in my PhD in 1997. And that continued through to about the year 2000. I was still writing up in 2001. At that point, I decided I wasn't totally sure what I wanted to do, whether to go into industry or go and stay in academia. So I did something a bit more of a halfway house. I joined a company called AEA Technology, which was the privatised offshoot of the UK Atomic Energy Authority, and worked there on fluid flow analysis. In 2003, I think I got a big break, and that was to go to the Northeast to work with a company called Lucite International, which used to be ICI Acrylics. And that was to work on a flagship project for them, a new route to methyl methacrylate. And this was a really good experience because I was lucky enough to take something through as part of a larger team from a test tube right the way through to a full-scale process. And I was lucky to see it. I was actually on the commissioning team, and it was great to see all those years of work being put into a process where environmentally, the byproduct of this new process was water, as opposed to the various wastes of the existing process. Following that time, I then went to work for Invista for a couple of years in the licensing part, and then I joined Johnson Matthey late 2013 to work on a bioprocess to existing petrochemical products. I've been there ever since. I've done various process development roles in various technologies. I spent 4 years in the corporate R&D centre in JM, and just recently I've come back into the licensing business unit where we're looking to catalyse a lot of the chemistries towards net zero. There are bits of the Roberts building I still recognise, despite the fact it's been sort of added to in various dimensions. It's been really interesting to walk around the undergraduate labs to see how some of the original equipment is still there, how it's been added to, so the fundamentals are still being taught. What is very interesting is some of the new labs, some of the scales that we are now working with. We seem to have gone down the scale in some of the very sort of small, almost molecular engineering. And it's great to see how that's evolving from not only a research perspective, but also from a teaching perspective as well. So we're really seeing a change there as we're moving towards looking at materials as well as just the classic things we have analysed in the past. So there's a real change in the 30 years since I've been here, not just in the amount of equipment, but also in the scope of the scales we're actually looking to look at. If we look back into, say, the mid-90s when I was a student, it was very much geared around the petrochemical industry, understandably at the time. We looked at very much steady-state processes. We always were looking at sort of guaranteed feedstocks over the fence, so to speak. Now that's changed. As we look towards catalyzed towards net zero, we have to deal with variable feedstocks, and not just in terms of the type of feedstocks, but also the actual availability. So process dynamics is coming much more inherently part of the process design than it was. We are also looking much more at the environmental metrics associated with our processes, the reduction in energy, That's become very apparent now, not just in the traditional economic sense, but also in legislation that we have to follow as well. So it's great to see that some of these environmental metrics are thought about right at the beginning of process development when we select those chemistry routes. And that can be anything from looking at the solvents, what solvents we use, the distillation trains, and if we think really outside the box, eliminating the solvents altogether. We've also got, looking at the mathematical modelling side of things, we've got a lot more tools available than we used to have. These are really embedded now, some of the high fidelity models in our engineering decision making. So if we go back to the 90s, we were traditionally looking at steady state simulators comprised of many simple models. Now we have much higher fidelity models in our process to give us really accurate information. This is beneficial just from a fundamental understanding, but it also allows us to go from very small scale experiments right up to full scale without necessarily going through an intermediate pilot plant. One of the things that is coming into chemical engineering is, as indeed many industries, is artificial intelligence and machine learning. It's interesting to see how that's coming in for helping us model things we don't necessarily physically understand. It's also very helpful in terms of predictions as we deal with some of these dynamic processes. But equally, I don't think that AI and machine learning is a panacea for everything at present. It's still very much in its infancy. It will become more relevant in chemical engineering, not just in terms of design, but also analysis, how we capture the data, how we analyze the data. And when we think about the huge dimensionality of the problem we face in chemical engineering, and particularly as if you go into dynamics, then this is going to become quite a relevant field. And we'll be looking for chemical engineers with data skills as well as the classic design skills. In academia, you have time to really think about things and maybe do a lot of research. In industry, it's much more pragmatic. You're expected to have those skills. They will upskill you as well in some of the practicalities to make very quick decisions. And we have to look at this in the broader context that when we're developing a technology, it has to be right for the economic environment, and therefore there are sort of timelines that we have to try and meet. And that was one of the biggest changes in working in industry. Equally, you get a level of education that you wouldn't necessarily get in academia, by experience and sometimes learning the hard way as well. The skill I would say I've taken away, one of the most useful ones, is tenacity. Because in the undergraduate level, yes, it's difficult. When you get to the postgraduate level, you won't necessarily find the answer in a book. You've got to have that drive to actually say, if I can't solve it one way, how will I do it another? And that has really filtered through into my professional career. And I'm pleased to say I'm still practicing that now as well. We hit challenges, but we just need to find a different route. When I started, you typically maybe have gone to a large chemical company and gone through the graduate scheme and naturally followed a well-defined path. I think things are different now. The scope is much wider. As we see chemical engineers moving into fields far outside petrochemical engineering, we look at alternative things like fuel cell manufacture and other advanced propulsion systems. Chemical engineering is very diverse, and the skills that students are picking up are very applicable into many industries. So my one piece of advice would be try and be diverse, be open to new opportunities, and importantly, be adaptable. There's a lot of opportunity out there. As we say, the world's evolving. It's not just heavy engineering anymore. If we can get those data skills into our young chemical engineers, then those fields are only going to expand.